Yes. I don't understand for this right now. I think I and we stopped where? Stopped here. Stein. 330. 28. Perfect. Just got the approval for the software, so I'm going to try to quickly send an email because this class will be perfect. So forward to um, 1 minute. Let's see if I can send it in 1 minute. I need the ATS approval. I will do it when you guys are working on your quiz. That way they can start processing it today. Okay. I can take any questions you might have before others join. I think we're left with just Christian, right? Do you have any questions on what I've covered so far? Yeah, I guess I already took all the questions, right? Yeah, I'm gonna try to do the quiz early, maybe in another 10, 15 minutes time, since the quiz, I set it up so it's just for module 2. And then in the next class, we'll do the first one on some part of module 3. So, okay, so I already discussed the previous slide at length, right? But I didn't say a lot on this. And I have videos covering all of this now, up to 3G, I think. And I assume you guys have watched it, right? Because I don't think whatever I discussed during the Zoom meeting is exactly what's in the video. No, those ones are more detailed. So here I just summarize and take questions. So any questions on this slide? Which one has a higher frequency, a higher frequency or velocity? Which of the sound waves has a higher frequency, the one from the lab or the one from the well log?
The lab.
The lab, and you can see the value here. So what's the value here in hertz? Is it 6 hertz? Is it 6 hertz or 10 raised to the power 6 hertz?
That's
So it's 10 raised to the power 6 hertz. So it's usually on the order of 1 megahertz. And I mentioned that in the videos. Whereas the one for the log is on the order of kilohertz. So this is here is 1E3, right? So this is about 6,000 hertz. And why are these guys? You observe that this is a lot lower. All of these curves are a lot lower than this, right? What's the difference? One is P wave velocity, primary or compressional wave velocity, and the other is secondary or shear wave velocity. And we're going to talk about those later in this module. So the variation here is smaller than here, but the trend is the same. And what's the trend? As viscosity increases this way, right? This is 1 centipoise, 10 centipoise. As viscosity increases, what happens to the P wave velocity? It increases, right? And that means the material is getting stiffer or less stiff.
Stiffer.
Yes, because sound travels faster in stiffer materials. So that's what's going on there. And the phenomenon which results in the lab stiffness being higher than the log derived stiffness is called what? The phenomenon that results in the lab measured stiffness being higher than the log derived stiffness is called
Dispersion.
dispersion. And the theory that explains dispersion is what? The generalized theory of squared flow, which is just this. And this I already explained using the tennis ball filled with water with a hole using that analogy. So that's exactly what's going on. Higher frequency, the material appears stiffer because the fluid is not able to dissipate the stress applied within a short time when you send in high frequency data. But if you send in low frequency, it gets dissipated and the measured value is much lower. And it's important to note that when looking at data from logs, data from lab, and from what other source? From seismic. Those are even much lower. The frequencies are on the order of 5 hertz to about 50 hertz for seismic data. Any more questions on this slide?
I wasn't able to watch the videos. I saw them that they were posted yesterday when I was logging off, and I've been busy today with the career fair and other classes. Just to let you know.
Well, you're lucky because quiz 3 doesn't cover that. Quiz 2 stops on module 2, but it's important to watch it so you can ask all the right questions that set you up.
Yeah. All right. Well, that's good.
Quiz 4.
Okay. I've watched through module 2, but I was kind of concerned. I was like, oh.
Yeah.
But that sounds good.
Okay, so you should still try to follow what you're doing now. The only thing is you'll be looking at it on the fly. And of course, at any time, if you have any questions on previous modules, you can always send an email. Okay, so I move on to the next slide. And I already explained this, right? The most important thing is this light gray is the dynamic loading stiffness. And dynamic just means the fluid is in it and you're using sound waves. Whereas the static is your triaxial test. And so the dynamic is the one that is susceptible to the dispersion effects, right? Because the sound waves could be high frequency. And the question is where the light gray, again, those are the dynamic, right? Those short lines. Whereas the full curve is from multiple tests, multiple triaxial tests. So when you're going up this way, you're loading. When you're going down, you're unloading. And when does the slope of the gray equal the slope of the static? Is it when you're loading or when you're unloading? You can see these slopes are different, right? That's why they cross. If the slopes are the same, they never cross. They are parallel, something like this. See, it's close enough to the unloading curve. So dynamic loading stiffness corresponds to stiffness from static loading, and that's what you see here. I also explained this. Do you know the answer to this question? Why are strains much larger when you perform the static test, which is on a core, in comparison to the strains in your entire reservoir? Who knows? This is how I figure out whether you watch the videos or not. This is just like revision.
Is this due to depending on what kind of test you have? Because you'll have, like, if I just have a small core and I compact it, it's gonna strain.
It's related to that in comparison to the reservoir. So it's size, basically. It's related to size. And we're talking about strains, right? What strain?
That's the change in.
This is volumetric strain. But if you're looking at just strain in one direction, say a linear stuff, it's just delta L over L. So if you're looking at a core and you're looking at linear strain in the axial direction, right? In this direction, well, what's the L for this core? A few inches or 1 inch, very small. So you're dividing by a small number, but your reservoir could be on the order of kilometers. So you're dividing by a big number. So when you're dividing by a small number, yeah, the strain will be much larger. But in the reservoir, you're dividing by a bigger number and the strains are small. And that's why the assumptions in the Cauchy stress tensor make sense, right? And what's the assumption in the Cauchy stress tensor? Strains.
Small deformations.
Yes, small deformations, and the deformation is related to the strain. The strain is a measure of the deformation.
But how does that have anything? Size doesn't have to do with anything. If something gets 5% longer, you can't necessarily say, oh, well, it got 2 inches longer. It just got 5%. And that's what strain is kind of measuring.
Yes, but this is just a note that when you do your strain measurements in the lab and you're recording 10% deformation, 10% strain, don't expect to see that much in the reservoir. You see that much because of the stresses you're applying on it, which is much more than what you would get in the reservoir. But again, yes, it's a percentage. So, except that nobody wants to report. I think the instruments are also, I mean, they have a finite amount of sensitivity. So you will want to get reasonable strain in your measurements, not a strain of 0.001%, which might be actually closer to the reservoir, because that is less perceptible with whatever device you're using to record that. And I also make this point, right? We are not just interested in the geomechanical property of the formation of interest. There is a couple of formations sitting on top of your reservoir of interest. And typically those formations are not productive, right? If they were charged with oil and gas, those would have been the target reservoir. And the reason we are drilling through them is because they don't have what we want. So that's the reason why we don't core them, because there is no commercial value that can be derived from coring it, and coring is an expensive process. You stop drilling, you go with a special bit, then a hollow kind of bit, you drill into the formation, then take the sample to the surface, and that's expensive. So it's normal that you're not going to have lots of useful data in the formations above the formation of interest. And that makes things a little hard. And that's why seismic data becomes useful. So the elastic properties we get from seismic might be I was going to say that might be the only source of data, but no, we also drill through those formations, right? So information from the well log and information from the seismic data will be the only source of information regarding the elastic property of the formations above the formation of interest, because no one is going to call those. So we know our understanding of those formations are much less than the formation, than our understanding of the formation of interest. I also make this point here that in weak or unconsolidated sands, loading introduces both elastic and inelastic strains. Another word for inelastic strain is what? That's the one that is not recoverable. So those are permanent strains or permanent deformation. But unloading is purely elastic. So when you're loading this way, there is no guarantee if you let go, it's going to go back on the same trend, which is exactly what you see. It rises up this way, but the slope is different going down. But if you load going down and no, you unload going down and you load right back, it's going to trace pretty much similar slopes, which is why you see this is very close to this. And that's saying it's elastic. Elastic just means reversible. Question?
I had a quick question. So if you're coring, or if you get a core and it had already been under some sort of pressure, and then you put it at that's like a similar pressure to what it is, shouldn't it be reversible since it already underwent the damage from that loading? If that makes sense.
I see your point. But the other problem is we think the core is representative of the state at which we took the core, but many times it's not. So just the mechanical agitation and all of that goes into place during coring can make your core not really representative of your reservoir. But yeah, if it has gone through that load already, say a particular stress value of say 5,000 psi, and when you perform your test in the lab, you only go up to 5,000 psi, yes, that will be reversible because it was loaded, the core was loaded to that pressure in the reservoir and unloaded when we brought it to the surface, right? So that unloading is reversible, which is what we're saying here. It's purely elastic. So when you load it back up to 5,000 psi, it's going to be fully reversible. But we don't stop at 5,000 psi when we perform our triaxial test, right? Because you want to know the yield stress. You want to know the rock strength. That's one of the critical MEM components. So to get to, or to obtain the rock strength, UCS, you're going to have to pressure it all up, apply enough stress until the material actually fails. And those stresses are much higher than what the rock was subjected to in the reservoir. So those additional loading steps will be irreversible. They will contain both elastic and inelastic strain. So that's a good question. So once you apply stress greater than the rock has already seen, then you could incur permanent deformations. Any other questions on this slide? Effective stress, I explained this already. This is your saturated porous medium. Saturated meaning it's filled by the fluid, reservoir fluid. If you take out the grains from the formation, you take out the grains from the saturated porous medium, what you're left is the fluid. If you take out the fluid, what you're left with is the solid skeleton. And the skeleton is not to be confused with the grains. The skeleton contains the pore structure. It just has been drained of the fluid. So we'll later talk about that. I don't want to get ahead of myself because it's on the next couple slides. So we can think of your saturated porous medium has been decomposed into these two components. And then we'll later use Hooke's law to describe this, and we'll use a Maxwell model, which is basically a combination of Hooke's law and the viscosity, a viscous fluid. So a viscous fluid plus Hooke's law makes up your Maxwell model, which we'll see in the next slide, I believe. I made this point here, which is that the solid skeleton can resist both normal and shear stresses. But how about the fluid? Can the fluid support normal stresses? Yes or no? Yes. Can the fluid support shear stresses? No. Shear it just shears continuously. So that's one of the main reasons why we partition them. And the stress applied on the fluid is the pore pressure. Right? They're both force per unit area. Pressure is force per unit area, stress is force per unit area. But this one is omnidirectional because it cannot support stresses. Another material that we talked about that doesn't support shear stresses is what? Who remembers? You remember centroid effect?
Yes. Yes.
Why is the stress higher in the shale than in the sand? Actually, we say pliable shale, which is shale that is so weak that it doesn't support any shear stresses. And that's why the pore pressure is lithostatic.
Is that kind of like unconsolidated, or I guess unconsolidated can't hold shear stress?
Yes.
But when you're talking about the centroid in the sand, would that be unconsolidated or?
No, I meant exactly what you said. I meant the shale. I just wanted to remind you by just mentioning centroid effect. So you think about the pliable shale and the sand. And the pliable shale is what is unable to support shear stresses. And the reason, how is this porous material able to support stress? You try to shear it this way, meaning you like fix an object on the surface and you try to pull it this way. What happens to the grains? They start to interlock and you have frictional resistance. That's how an object is able to support shear stresses, but you can't have that with water, right? It just shears continuously. Same with pliable shale, weak and unconsolidated. So you slide it up, the grains just continue to deform continuously. And that's the important point there. And that's precisely why this is isotropic. Your pore pressure is one value, it's a scalar. We want it to look like your tensor so that you can add it to your effective stress or subtract it from your total stress, which we'll see shortly. And so we multiply by an identity matrix, and an identity matrix is just once on the diagonal, 0 elsewhere. So you will see this expression in your definition of effective stress. So shear strength of fluids is 0. Shear strength of pliable shale is 0. Any question? You can stop me at any point to ask questions. And now I begin to introduce effective stress. If you apply a stress sigma on a unit of your porous medium, saturated porous medium, you already know there are two components, right? The skeleton and the fluid. Well, the total area of this cross section, which is what the force per unit area acts on, the stress, that area is total area. But you can see that some of it is this small yellow areas, right? Which is the area of the interface between two sand grains. So if you add up all the yellow areas, what you have is area of the skeleton. What is left, meaning it's AT minus A skeleton is a fluid, it's area of the fluid, right? All the blues are the areas of the fluid. So the force per unit area you are applying gets partitioned into those. And that stress that acts through only the yellow areas is called the effective stress. That's the stress that acts on the skeleton and tries to, if it's compressive, it tries to compress against the skeleton. The pore fluid, the stress that acts on the fluid is what becomes your pore pressure, because it's force per unit area, but inside the fluid. And that's the concept introduced here. And effective stress could be written out fundamentally in this manner. This is not the way we use it. This is within the context of AT and AS and AF, right? All we have done is to add some scaling factor right here. So in the simplest form, if this parameter is just 1, which is what you see, right? As AS becomes smaller and smaller, you can see AS is very small compared to the total area, right? So this, we can neglect this. This tends to 0, and it's essentially 1. And what you have is the simple effective stress, which we had talked about before. This is the total stress you apply to the rock, and you've partitioned it into effective stress and pore pressure. You can see if you take it to the other side, it's just effective stress plus pore pressure. That's what your total area is. And because we are in the oil and gas business, compressive stresses are positive. Compressive strains are also positive. And I explained here that effective stress is the component of the stress taken up by the soil skeleton. Pore pressure is compressive. And so it will be positive when you're using our oil and gas nomenclature. How do we think about pore pressure being compressive? When you apply the stress on the formation, the pressure of the fluid increases. When the pressure of the fluid increases, it pushes against the porous medium, right? So it compresses the solid, the skeleton, and that's why it's considered positive all the time, regardless of your unit. So regardless of whether you're working with the engineering convention or the oil and gas convention, pore pressure will be compressive. And so we will need to change the sign in front of this if you're using a different unit, because we will always assume pore pressure is compressive. And you know, nobody talks about pressure being minus 5,000 PSI. The fact that you are working with engineering convention or you're working with oil and gas convention, we will still treat pressure as a positive value. And so the sign in front of it has to change to be coherent with the definition of the effective stress. And that's the question I'm asking here. Yeah, this will become positive if you were to do the same calculation in the engineering unit, and you will see that shortly. So that was simple effective stress. The scaling factor was 1, right? Simple effective stress is total stress minus pore pressure times identity matrix to convert it into a tensor. That's simple effective stress. And it works for weak and unconsolidated formations. In consolidated or compacted formations, what we do is to multiply by the Biot's coefficient, which is written as alpha in most publications. Sometimes you see it written as B. It's all the Biot's coefficient, and this is the definition of the Biot's coefficient. What is K? Bulk modulus of the skeleton. And the skeleton is the same as the drained material, right? So sometimes it's referred to as drained bulk modulus. How about this one? The bulk modulus of the actual grain, right? I already established that the porous medium, the skeleton is different from the sand grain. So which one do you think will be higher? The one for the sand or the one for the skeleton? The sand grain will be higher. And so this ratio will be less than 1. And you're taking out that number from 1. And that makes Biot coefficient less than 1. And that's what we use as the exact effective stress. And it's called exact because it is exact for the problem of volumetric strain. And there are derivations of this and this stuff in the literature, which is beyond the scope of our course. But that's why it's called exact effective stress. Sometimes it's just referred to as modified effective stress. And again, it applies when your rock has been consolidated. And when porosity is usually small. So Terzaghi worked on unconsolidated sands, so he was able to get by with this simple effective stress, which assumes alpha is 1. But for most rocks, it's much less than 1. For most rocks, it's about 0.6, 0.5, thereabout. For shale, it's much smaller. Why? Porosity of shales are much smaller, right? As porosity reduces, alpha reduces. How do we know that? Yeah, you can get that from this definition of Biot coefficient, right? If porosity is 0, that means there's no pore space. That means the skeleton equals the grain, right? So that's when is the least. And in that case, this will be 1, and 1 minus 1 is 0. So that's the other, that's one extreme. The other extreme, when porosity is as large as can be, and I believe you guys know that the theoretical maximum value for porosity is what? About 47 point something percent. How do you get the theoretical maximum? Put a sphere in a cube and calculate the pore space left. The sphere is the geometry that gives you the most porosity. So when you calculate that porosity, it's going to be 47 point something. So at that value, at the maximum theoretical porosity, that's when K is much less than Ks, right? So if K is much less than Ks, then the ratio of K to Ks tends to what? 0, right? In the limit where porosity becomes maximum, K over Ks tends to 0, and alpha becomes 1. And the moral of the story is, if you have very high porosity systems on consolidated sands, alpha will be close to 1. In the other extreme, it's closer to 0. And Biot's coefficient controls the degree of coupling. I explained this already in the video, and it basically gets multiplied by a parameter in the governing equation for flow, and you can see it scales it directly. If it's 50%, then it's half of the stress that gets transferred to the fluid problem. And if it's 1, it's 100% of that. So it controls the degree of coupling between your mechanical problem and your fluid problem. If porosity is 0, yeah, alpha will be what? Close to 0. If porosity is 0, K equals Ks1, yeah, alpha will be 0. And there will be no pore pressure influence. And the other extreme is what I explained here, which will have the maximum pore pressure influence. Any question on this?
Do you want us to take this in account during our homework or no?
What do you mean by this?
Whenever we're calculating the effective stress, do you want us to use like assume an alpha value, or would you want us to go through by like porosity and kind of put where we think it should?
Yeah, just use 1. So use simple effective stress. Once you see I don't give you a Biot coefficient, then it's simple effective stress. If you have a Biot coefficient, then you use this.
For when you're saying pore pressure, are you necessarily saying hydrostatic?
No.
Okay.
Unless we say hydrostatic. Pore pressure is the pressure of the fluid in the porous medium. It could be hydrostatic, it could be overpressured, and in some weird cases, it could be under pressure.
Okay.
Good. Here I just show lab values. I'm not going to talk much on this because I already explained it in the video. And this is the one I wanted to make clear just because people get this modeled up. They say we are using the engineering convention, but they are not using this equation. Or they use this equation for effective stress, but they don't consider that the strain needs to be, the sign on the strain also needs to be corrected. And if you're developing your own code for geomechanics, you continue debugging and chasing the code, you spend days and you just don't get the result because of the lack of understanding of this sign convention. So this thing is very important. And more so it's important because we are, petroleum engineering is in the oil and gas, but everybody else uses engineering convention. Your Abacus is designed using this sign convention. So when you start to do the labs, you will start saying, oh, looks like this is a little different. You want to put compressive stress, then you have to put minus in front of the number because you're using Abacus. Whereas in the oil and gas convention, you just use positives for compressive stress. So what I'd given you before is this equation right here, right? Because I had written it in terms of effective stress. Effective stress is this minus PI, right? And compressive stress is positive. So if I want to apply a total compressive stress of 50 psi, just random values to see how it works out physically, I put plus 50 because 50 is compressive. Effective stress turns out to be 30. I put plus 30 because it's compressive. Pore pressure is compressive, but the sign doesn't show up in the number you put. The sign is taken into consideration here. Because whether you are in engineering convention or the oil and gas convention, nobody is going to model pressure as being a negative number. So 20 is here. The sign on it being compressive is already positive to account for that. So the sign on pressure is the same as the sign on the stresses, right? Because they are all compressive in this case. This is where it gets interesting. So engineering convention, tension is positive. So compression is negative. So I want to model the same system, 50, 30, 20. So I need to do minus 50, right? Like I said, because it's compressive. Tension is positive. Same here. Those are pretty straightforward. This is where it starts to get tricky because you can be thinking pressure is compressive. So I put minus in front of it. If you put minus, another minus, then you double correct and it becomes positive, which is wrong. So the fact that pressure is compressive is already taken into consideration by this minus sign here for this convention. So we're just going to use pressure as it is. We don't change the sign on pressure. Pressure is pressure. It's 20 psi. Supply the 20 psi. The sign takes care of business. And now everything is in the right units. And this will be the effective stress, making effective stress the subject of the equation, making it the subject of the equation here. Effective stress is actually the sum of the total stress and the pore pressure. And this is the other part that some forget, and they implement it in one way and the code doesn't work. And it's the sign. When you're in the oil and gas convention, when you have done sigma prime as sigma minus pore pressure, you have to put a minus in front of your equation for strain. But here you don't. And this equation for strain, I hope you know that I is the x direction, J is the, so you're basically saying differentiate displacement in the x direction with respect to the y direction. That's the J plus the uy dx and half of that sum. That's your minus and the petroleum engineering convention. That's the gist on this slide. Any question? This is actually very important. If someone doesn't understand this, yeah, and is using a software that's using this convention, then it's just going to be struggling. Hooke's law, which is one of the constitutive equations for, it is the one of the constitutive equations for what? For linear elasticity. So we have implicitly assumed that all the deformations are what? Reversible, right? The deformations are reversible. So linear elasticity is one of the basic constitutive relationships. Other constitutive relationships, viscoelasticity, viscoplasticity, plasticity, right? This is the simplest and most commonly used. And that's your Hooke's law. Stress equals the stiffness matrix multiplied by a strain tensor. And this is 3 by 3, second order tensor, right? We already talked about these two. I'm not sure we've talked about this. This is 3 by 3 by 3 by 3. So is what order tensor is this? Your stiffness matrix C is what order tensor? One person has to get it.
4.
Huh?
4.
4, correct. Because this is second order, right? We already said one value, a scalar value, 0th order. A vector, which could be 3 by 1, for instance, is first order. And 3 by 3, second order. 3 by 3 by 3 by 3, fourth order. So this, in the full form, without accounting for symmetry yet, has 9 components, right? We talked about that. Then later, when you account for symmetry, then it becomes 6 components, right? Because 3 components below the diagonal are redundant. So how many components are in this elastic stiffness matrix?
$81.
81 is 9 times 9, right? 9 times 9. But you account for symmetry here, then you write this in the Voigt notation right here, right? As 6 by 1. You do the same thing for your strain. So you've only written out the 6 useful parameters. The other 3 are these repeated, right? So it's now 6 components instead of 9. Just by rewriting that, you also get to rewrite this one, right? Because now you're trying to do 6 by 1 equals 6 by 6 times 6 by 1. It's a matrix vector multiplication. So this has to be 6 by 6 because you're going to be multiplying these 6 items by these 6 items to get to do your mathvec, matrix vector multiplication. So the dimension of your elastic stiffness matrix has reduced now to what? 6 by 6. How many elements are in a 6 by 6 matrix? 6 times 6, right? Which is what? 36. So the same system that was made up of 81 components can be written out, is now made up of 36 components. Just because we've chosen to use the Voigt notation, we've accounted for symmetry in the stress and strain, remove the redundant elements. Now it's 6 by 6. The interesting thing is this is also symmetrical. So this 6 by 6 matrix is also symmetrical. So everything below the diagonal can be removed. And I'd like to ask this question. And the question is, how many independent elements do you have left? How many elements do you have in the matrix left? So right now it's 36, but this one is not useful. The one below it, everything below the diagonal is redundant. So when you take out all of those, what's the number of elements you're left with? Easiest way to think about it. How many do you have on the first column? Just one, right? How many do you have on the second? 2. So 1 plus 2 plus 3 plus 4 plus 5 plus 6. That's the answer to the question. So 1 plus
21.
yes. So based on the symmetry of the elastic stiffness matrix, you only need 21 components. Based on the symmetry of the stress and strain, you went from 81 to 36. Based on the symmetry in the stiffness tensor, you've gone from 36 to 21. And that's what you're going to have. You will need 21 independent elastic components to completely describe a linear anisotropic solid. But if you now start to make some other planes of symmetry, some assumptions regarding the planes of symmetry, like we have talked about for transversely isotropic solids, which is symmetrical about the z-axis, right? It's symmetrical about the z-axis. So anywhere you go in the x-y plane, the material is isotropic. Stress in the x direction equals stress in the y, but it's different from overburden stress in the z. So it's symmetrical about the z. When you make that assumption, then you go from 21 independent components to just 5. And when you assume you have an isotropic solid, you actually reduce that to just 2 components, which could be any pair of elastic moduli, like Poisson ratio and Young modulus, or bulk modulus and shear modulus, or any combination of those parameters. And here I'm just showing how you do matrix vector multiplication, which I already explained in the videos and it's high school stuff. Any questions on this?
So I'm not gonna lie, that's not really all that clear to me. But like I said, I haven't watched the video. Do you do a similar, like, do you say similar to what you just went over in the video?
Yes, but slower. So what part is not clear?
I really don't understand how that's a fourth order matrix.
It's all about how many directions can you have more than one value. That's what determines whether that's the number of dimensions. The number of dimensions in your problem is the order of the tensor. So 1 by 1, you don't have more than one item. That's a scalar. It's a 0th order tensor. 3 by 1 or 5 by 1, n by 1, you can have multiple values in one direction, right? So that's first order matrix, or first order tensor, 3 by 1. So you can see there's only one dimension where it's more than 1. Then 3 by 3, how many dimensions is it more than 1? 2. That's a second order tensor. And now this one has 3 by 3 by 3 by 3. So it's fourth order because there are 4 dimensions to it. So that one is.
I don't know how you would write out. You can visualize a 3D matrix.
Yeah.
And I don't think that there's a way to visualize a four-dimensional or fourth order matrix. But
yeah.
Why do you choose to write it out? I guess that's really the only way to write that out.
Yes, and that's why this is a tensor product. So that's the way to write it out in the matrix format using linear algebra. But like you said, we find it difficult to visualize a 4 by 4. That's why we use the void notation, so that it now becomes 6 by 6 instead of 3 by 3 by 3 by 3.
Okay.
So yeah, it's the void notation is to overcome the difficulty in visualizing it. But you can do this fourth order tensor in matrix, right? In MATLAB, all they do is they create your 3D, which you can visualize. Then all of that is just one slice.
Right.
Then they replicate that 3 more times. So MATLAB can do this calculation actually, but it's also not efficient because you can see you have 81 components, but you only need 21. So what a waste. So that's what you also benefit from void notation. So you benefit from 2 levels of symmetry. First, the symmetry in the stress and strain, and the symmetry in the in the stiffness matrix. Any other questions on this slide?
This might be a little bit repetitive or not quite on focus, but when it has 81 components, like an example of one of those components, could it be like stress in the negative x direction, and then you also have another component of stress in the positive x direction, which is the same thing?
So it's a stiffness matrix. So an example could be Young modulus in the x direction. Another example, Young modulus in the z direction. Young modulus in the y direction. Then you go to Poisson ratio. Poisson ratio in the x direction, in the y direction. And you will see examples of those on the next slide. But definitely not for 81 components. So we start out with isotropic. How many independent elastic properties do you need? Elastic modular, just 2, right? Right here. And what are those 2 in this case? Young modulus and Poisson ratio, right? So it's still the same dimension as 6 by 6, but to fill up that matrix, you will only use 2, E and nu. And it's just repeated here, but with a specific form to it. And this is what we use for linear elasticity. And again, you can use any 2. I mentioned in the video that I will show how to convert from any 2 to any 2. So that's really very straightforward. Just Google Hooke's law and choose the result that comes out for. There is nothing to it, that's why I don't even bother trying to cover it here. Once you see Hooke's law, Wikipedia, no, you grabbed the wrong one. But you got to see what Hooke looks like for a second. Just scroll to the bottom. You're looking for a table. It's also in some textbooks, but nothing special. Once you have the elastic modulus or 2 elastic moduli in any form, you can convert to any form using this. So KE. So if you are given KE and you want, let's work with what is more realistic, KG, right? Bulk modulus, shear modulus, the third row. And you want EV, meaning Poisson ratio and Young modulus. Then you'll get Young modulus from this equation, all right? E, and you go to that KG stuff. So it's in terms of K and G. It's very difficult to miss it because it has to be in terms of what you want. And you go down to the Poisson ratio, and it's this, also in terms of K and G. This is the M modulus in terms of K and G. First Lami's constant, that's the lambda. First Lami's constant, this is it, in terms of the same K and G. And second Lami's constant, which is typically written as mu, is the same as G. So important to not get confused. Any time you see mu and they're saying is the second Lami's constant is actually the same as G, which is shear modulus. So the second Lami's constant is shear modulus, but the first Lami's constant is by itself. And those are the 5, how many are the 6 parameters? You already know E and nu, Young modulus and Poisson ratio. You already know bulk modulus and shear modulus. M modulus is the one that's less known, and you will see it shortly in this module, and the first Lami's constant. So that's how you can convert from one to the other. So it's not really important. All you need is any 2. They are all independent. So these are the slides, but I want the PDF. Good. Transversely isotropic, I said there were 5 unique parameters. This is the system, but C1, C2, C11, C12, C13, you can now get by inverting this. So when you're looking at the Hooke's law, the way I wrote it out, C is the elastic stiffness matrix, right? Well, sometimes we work with the inverse of the elastic stiffness matrix, and that inverse is known as the compliance matrix. And that just means maybe you're calculating epsilon. You know, if you use Hooke's law as is, you're solving for stress given C and epsilon. Well, if you want to solve for epsilon, given stiffness matrix and strain, we can concretize it, right? You can also do this C inverse. And this is just linear algebra. Multiply both sides, pre-multiply both sides by C inverse. So C inverse times C goes away and you're left with epsilon, and you're on the left-hand side, you have C inverse sigma. And this C inverse is your compliance tensor. And that's what is given here. And you can see the independent parameters here. I count them out in the video. Epsilon in the Young modulus in the X direction, in the Z direction, Poisson ratio 2, 1. These are all shear stuff, right? 3, 1. So on phase 2 in the direction of first axis and so on. So 1, 2, 3, 4, and the last one is mu 2, 3, which is shear modulus on the Y phase acting in the Z direction. Any questions here? I already explained the axis of symmetry for transversely isotropy before. So shales and most reservoirs are transversely isotropic. Why? Layering. We already talked about that before. And the axis of symmetry is what? Z-axis. I mentioned that earlier in this video. Are we here already? Okay, I think this is what my video has covered so far. But I can just make a few more comments. What's time? 4:25. And class ends 4:50. Now let's take a break and let's go ahead and do our quiz right now. Then we can continue from there. So already signed in. Oh, actually, just see it on the other computer where I signed in. Not prepared. So 42, 41. I'm doing it on the other computer, so it's going to be available. It's in module 2, right? Quiz 3 is under module 2. Show. So you can refresh and start quiz 3. I gave you more minutes, 5 questions, but 8 minutes. Are you all done?
I'm done.
So timing okay this time or too much? Is the timing is the time allotted too much? Okay. Do you guys like the questions? I think I love this format. It's you can put in a lot of stuff and it still makes sense, even though the exam is open book. The previous true or false format is just to water down. So yeah, I'll stick to this format. Harun,
Yes, Dr. Fahmi.
yeah, so we're still having issues setting up the remote access. So I'm like, maybe we shouldn't go ahead and discuss the labs until we have access. That
Okay.
way they don't just learn it and forget because they're not able to practice. So I'm working with Chris and also working with the license renewal. So license renewal is another problem, but the problem we are having right now is access to the computers.
Okay.
But if some of you are on campus, you can just walk into PFT 2243 and get direct access. But I still don't feel comfortable assigning it until we have that access. So I'm putting pressure trying to get this all sorted out. So you sent me a video, Aaron.
Yes, 3 videos for
So what
three
for what?
for 3 part of first lab.
Okay. Do you want me to go ahead and upload those?
You can upload, but it will be nice if you can first have a review. Like if I miss something.
No. You guys are the experts, so I rely on I rely on the TA to do the lab, yeah.
Okay. Yeah. I actually I checked, so I tried to show step by step, and also try to explain the problem first. So if I miss something, then I can discuss on the class.
Yeah, and the other thing is you can do it exactly the way I'm doing mine, which is you upload the videos, then you can be available to take any questions they have after watching the videos. That's why I was asking to upload the video. So I'll take a quick look through it, but there's no way I can.
Okay.
Yeah, I think you have more experience using Abacus, so I'll take your word on it. You own the lab, so you also do the grading of the lab. And so we'll upload the videos, then we'll have a session where you can take questions directly if they have any challenges modeling the problem. So,
Okay.
so I'll just add a section on the Moodle page, just the same way I'm putting all the videos, then there will be videos for the lab, and I'll put comments the way I've been putting comments on everything I upload. I think that's how we're gonna. Well, but we'll continue with the lecture material. We have a lot to cover in topic 3. And I hope you guys are ready for the next quiz. So there'll be a quiz tomorrow that will cover everything I've uploaded through today. So I'll definitely upload more stuff, right, for next class, which you should also watch. But I'll try to keep it up the way to slide 19 right here.
So quiz on Thursday too.
Yes.
Good deal.
We have 10 quizzes. We're trying to get to, is it 10 or 12? Whatever number of quizzes I put on the slides. I'm not going to get all the way here, but I'm still going to cover it again in the video.
I don't know about Jake and Isaiah, but I kind of would rather do quizzes more often. I know you have like a certain amount in the syllabus, but just while stuff's fresh on your mind and test stuff.
Yes.
But I just kind of want to give you feedback there.
Yeah, I like that feedback because that's what I started thinking about. I came up with this multiple quizzes approach after my first class. So the first class, I thought, yeah, I noticed people weren't reading the slides and all at the level of details I test at with these quizzes, right? So I figured, okay, maybe the first time I did a quiz, everything counted for just 10 points. So it doesn't really hurt your grade, but it prepares you forces you to think more deeply about the problem. So I also love the quizzes, but it's a lot of work though. Creating the quizzes for every class. But I'll keep doing that. So since you like it, yeah, sure, I can give you as many as you want. I can probably do up to 13 or 14, then choose best 10. That's what I do with my 30, 20, 61 class. So even if you don't do well on a few, those grades get knocked off. But it encourages more connection with the course material. So yeah, thanks for the feedback. I'll get you more quizzes.
Can we do best 5 quizzes?
Best 5? Do you want 6 quizzes or so? Yeah, I think I set it up for best 10. But yeah, I can give you a little more since no one will complain about that. Yeah, and I'll still pick the best. I'll pick the best number I put in the syllabus. That's what I can't really change without having issues on the syllabus. Yeah. And now I started thinking, what will my midterm look like? If I already asked all my difficult questions in the quiz. Well, yeah, I'll have to be more creative. All right, any other questions?
I actually had one more question. I thought of it during the quiz. It was about that strain matrix. I've never seen that in that way, where that's EX, EY, EZ, and the 2EX, 2XY and stuff.
Yeah.
Is it just the same image as that that stress matrix? Like,
Yes.
physically just look like that? Okay.
So this is just straight matrix. XX, XY, XZ. Then Y starts YX, YY, YZ. Then Z starts ZX, ZY, ZZ. That's it. I'm not sure if I still discuss it again. So that's your strain matrix. It's just like your stress matrix, but it's strain. And later we'll talk about the trace. Yeah, I think I have it actually. Now that I think about it, it's one of these slides. The trace of a matrix is the sum of these 3 values. And what is that? What's the sum of these 3 called? Volumetric strain. So volumetric strain is just the sum of the normal stresses. You know, the normal stresses are what lie on diagonal. So that's your volumetric strain. Whereas we have mean stress. Mean stress is also the trace of the stress tensor or stress matrix. Is the trace of it, but divided by 3. So this is one weird thing to watch out for. The mean stress is a mean. It's a third of the sum of the normal stresses. But volumetric strain is just the sum of the 3. You don't divide by 3. That's just one point to note. All right, any other questions? In that case, see you Thursday and be prepared for quiz 3.